Welcome, I'm Professor Luoma, and in this video we're going to go over some problems from Chapter 3, the Introduction to Probability chapter. First problem, let's suppose that the events E and F are mutually exclusive, and furthermore, we know that the probability that E occurs is 0.4 and that F occurs is 0.5. We want to find the conditional probability of E given that F occurs. Now when you're working a probability problem, you want to first make sure that you extract all the information that's given to you. Now obviously we're given two probabilities here, 0.4 and 0.5, but we have to make sure that we don't overlook this other critical information that tells us that E and F are mutually exclusive. Now there are a number of formulas regarding probability and also definitions. On the midterm and on the final exam, I allow you to have a 8.5 by 11 sheet of paper that you can write anything on. I recommend you start preparing for those tests by creating a formula sheet, note sheet, as you work through these sections. So in particular, what we're going to reach for is the definition of mutually exclusive. Mutually exclusive events are events where the probability of them both happening at the same time is 0. That is, the probability of E and F occurring is 0. So we actually have three pieces of information given to us at the top of the page. So now let's go and address the problem that we have, the probability of E given F. Once again, we need to reach for a definition which is in the form of a formula. The probability of E given F is the probability of E and F divided by the probability of F. So we want to make sure we know that formula, and then we can reach for it and use it. But we're going to have a very simple answer to this, because notice that the numerator is essentially the definition of these events being mutually exclusive. So the numerator is 0. Well, the denominator is given to us as 0.5, but 0 over 0.5 is just equal to 0. And there's our answer to this problem. So just knowing a couple of definitions allowed us to get through that. Now I recommend as you do probability problems that you make sure you use the relevant definitions and formulas, because sometimes your intuition will lead you astray. But before we advance to the next problem, I'd just like to show you that this answer actually makes perfectly good sense. Now let's look again at what we were asked, the probability of E knowing that F occurs. Well, look, if these are mutually exclusive events, then they can't both occur at the same time. So if we're told F occurred, then could E occur? No, of course not. So it makes perfectly good sense that this answer would turn out to be 0. Now let's go to our second problem. Here we're told that J and K are independent events, and also that the probability of J given K is equal to 0.3. Now if J and K are independent, it tells us two things, and this is really from the definition of independence in this chapter. It says that the probability of J given K is just equal to the probability of J. In other words, knowing that K happened doesn't really tell you anything additional. Now, it's also true that if you swap these around, that also is a consequence of independence. That is, the probability of K given J. In this case, you're given J, but it really doesn't tell you anything additional. The answer is just the probability of K. So there I just wrote for you the two statements that essentially come from the definition of independent events. And now let's tackle the problem in question here. Probability of J. Well, let's look at what we have to see if we actually are given the answer somewhere here. Well, there's a probability of J. So that's what we want to find. So notice we know that that equals the probability of J given K. And look, we're told that that equals 0.3. So there we go. Okay, now I did a lot of work to get at something that hopefully you'll get to the point where it'll be obvious to you, if you're not already there. We're told that the probability of J given K equals 0.3, but since they're independent, K really doesn't tell you anything additional. So that just plain J given K is the same as the probability of J. End up being identical. So make sure you understand independence and mutually exclusive and the fact that they're not the same concept. A lot of students somehow get confused and think they're identical. All right, the next one I have a silly little problem here. Suppose that Count Chocula is allergic to chocolate and nuts. He attends a party, yeah, the Monster Mash, right? Where 36% of the cookies contain chocolate, 12% of them contain nuts, and 8% of them contain both chocolate and nuts. So let's first define our events. We'll let C refer to chocolate, cookie contains chocolate, and N refer to nuts, the cookie contains nuts. Part A, I just want to state the probabilities that were directly given in the problem. In other words, summarize the information. So we are given the 36%. That is the probability that the cookie contains chocolate, right? Probability it has chocolate is 0.36. And then the 12% is the probability that the cookie contains nuts. So 12%. And then we have the information about 8%. Now what is that? That's the probability it contains chocolate and nuts. And that is 0.08. First, let's find the probability of not C. In other words, the cookie does not contain chocolate. Well, that's pretty easy. The probability that something doesn't happen is 1 minus the probability that it does happen. So that would be 1 minus 0.36 would equal 0.64. Notice 0.36 and 0.64 add up to 1, as they should. You either have chocolate or you don't. Now, not N would be 1 minus the probability of N. These are what we call complementary events, N and not N. So that would be 1 minus 0.12. I didn't need a parenthesis there, sorry. Which would be 0.88. And 0.88 and 0.12 add up to 1. Now those were pretty simple questions. Let's do a couple that are a little bit more advanced than that. I just repeated the information at the top of the page so we'd have it handy. Find the probability that a randomly chosen cookie contains chocolate or nuts. In other words, it would be a cookie that the count can't eat. So let's write that first as a statement. The probability that we have chocolate or nuts, C or N. And make sure you're always very careful. You write down or and as the problem calls for, because we have different ways of computing and or statements. Now we have a formula, again from this chapter, for the probability of one event or another event. The formula reads that it's the probability of the first event plus the probability of the second event minus the probability of C and N, that is the and statement of both of these. And let's see what we have. Well, probability of C, I of course wrote it down on the previous page, but you can look at the top of the page here. That's our 0.36. Probability that the cookies contain nuts was 0.12. Now notice right now 0.36 and 0.12 give 0.48. The reason we have to subtract something is we have an amount that we're counting twice. The cookies with chocolate, some of those have nuts. The cookies with nuts, some of them contain chocolate. In both cases, we're counting the same identical cookies there, so we have to subtract away the and statement, probability of cookies and nuts. And let's see, that is the 8%. And so it was 0.48 minus 0.08. And so that probability is 40%. So the count could not eat 40% of these cookies. And let's go and look at one more type of problem here. If you've already looked at the homework, you've seen that there are some problems involving what are called contingency tables. Let's suppose this table gives numbers in the millions. So notice we have males and females. We have never married, married, widowed, and divorced. The rows should add up to the totals you see on the right. The columns should add to the totals you see at the bottom. I double checked them, so they should be good, barring some silly typo on my part. First, find the probability that a person is a male. Now we're going to set this up as a fraction, and we're looking at just all people, okay, persons. There are 219.7, of course, millions, of people that we're considering in this table. Now, the probability that a person's a male, we want to look at how many males there are. And in that case, we have, out of the 219, we have a little less than half of them, it looks like, are males. Now, if you divide that and expand it as a decimal, I believe most of the homework problems had you give it to 4 decimal places. There might be some exceptions, but I'll just go with that as I'm working these problems. It's not a little less than half, 0.4834. Now, second one. Find the probability that a person is widowed. We're just looking at persons, so everyone again. The denominator is 219.7. And we're not talking about just males or just females. We're just talking about all people. Out of those 219 million, notice that the widowed people would represent the would be represented by the 13.9. And when I divided that, I got 0.0633. So a relatively small percentage population here are widowed. Let's do a few more parts to this. Same table here. Now find the probability that a person is male and married. Okay, so again, we're looking at just persons. We're generic there. We're essentially looking at all the people. So the denominator is, again, the total amount, 219.7. And let's see, male and married. What number here would represent that? Well, it looks to me like it would be this number here, wouldn't it? That's where the males and the married meet. So that would be 63 plus million people are male and married. Divide here to get this probability, 0.2895. Next problem, find the probability that a person, just looking at a random person, so we're going to use that 219 plus again, is male or married. Okay, now we have an or statement there. That will be found as the probability that someone is male plus the probability that someone is married minus the probability that we have male and married. So let's work these out. The probability that a person is male, let's see, that would be 106.2, because that's how many males there are out of the total population. Next, same denominator, what's the probability that a person is married? Well, here I would be grabbing the 127.7. That's how many married people we have total out of all the people. And then we would have, for the last fraction, out of all these people, how many are male and married? We should know that number because we used it in the last problem. That is our 63.6. If you do the arithmetic here, add the first two numbers, subtract the third, then do your division. What I got was 0.7751. I actually have two more parts of these problems that we'll go to, and that'll finish this video. I have some problems involving conditional probability. Find the probability that a person is married given that the person is female. So here's how we would write this. Probability of married given, we write that straight bar, given that the person is female. And what I want you to notice is the denominator here is not going to be the 219.7 like it was in all the other problems, because now the denominator is just going to refer to the number of females. See, we know the person is a female. So a conditional probability changes your denominator. Now, how many females do we have total? Well, let's see. We've got 113.5. So essentially we're looking at this column here since we know the person's a female. All right, now out of that, how many of those are married? That would be 64.1. For this, I got 0.5648. Now, one last problem to do. Let me erase this so we can again go and circle relevant information. This time, please notice that it's like the reverse of the previous statement. Find the probability a person is female given that the person is married. And generally speaking, when you turn around the things, you're not going to get the same answer, generally speaking. Now this time, we know the second part. We know that the person is married. So you see, this is what we know we're restricting ourselves to, just married people. And so the denominator, the number of married people, is 127.7. Now, restricting ourselves to that second row, how many of those are female? Well, that looks like it's the 64.1. And so doing that division, 0.5020. If you've ever heard the phrase contingency table before, it probably had to do with insurance. In insurance, they use lots of contingency tables. In order to figure out how much they need to charge someone, they look at things like, okay, what's the life expectancy or the probability of death if a person's a male? What's the probability if it's a male who smokes? And you can see that all that information can be summarized in tables and allows people to very quickly analyze the various probabilities. Okay, that ends this one. I hope this helps you some. Good luck, folks.